Somewhere about 1,400 light-years from Earth, a world is being pulled out of shape by the gravity of a dead star. It is not round, it is not calm, it is not even orbiting something that looks remotely like a sun. It races around a pulsar in less than 8 hours, whipped by radiation, stretched into something closer to a lemon than a planet, wrapped in a sky so chemically strange that astronomers stared at the data and asked the most honest scientific question possible. What is this? That reaction matters because telescopes are supposed to turn mystery into clarity. James Webb did the opposite here. It looked at a planet-sized object and found an atmosphere almost no one expected to see. Not water, not methane, not carbon dioxide. Instead, molecular carbon, the kind of chemistry that should not dominate a world like this under any familiar planetary recipe. And once that signal appeared, the problem got worse. Because if the atmosphere is real, then the planet's history becomes almost impossible to explain. If the history is real, then the object may not have formed like any planet we know. And if it did not form like a planet, then why does it look so much like one? That is where the unease begins. A dead star the mass of the sun but the size of a city. A companion roughly in the planetary mass range. A sky full of soot. A possible interior where carbon may crystallize into diamonds. A system so violent it sounds invented, yet so cleanly measured that scientists cannot dismiss it as noise. For a moment, it felt like modern physics had missed something. Not because the laws of nature were broken, but because one object had slipped straight through the story we tell about how worlds are supposed to be born. And the strangest part is this. James Webb may have found it precisely because the star at the center is almost invisible to the telescope that was never built for systems like this. That sounds backwards. It is backwards. And to understand why one impossible-looking planet has astronomers rethinking the border between stars, planets, and cosmic leftovers, you have to begin with a machine that was built to see the faintest heat in the universe, and a graveyard of stars where planets were never supposed to feel at home. James Webb was designed to study the deep infrared universe, to catch ancient galaxies, newborn stars, and the chemical fingerprints of alien atmospheres. But one of its greatest powers is not simply seeing far away, it is seeing what other observatories cannot separate. On ordinary exoplanets, the parent star overwhelms everything. The planet is there, but drowned in glare. Webb changes that game by teasing out faint signals hidden in light. And in this case, it found something almost absurdly perfect for that job. The planet known as PSR J2322-2650b circles a pulsar, a rapidly spinning neutron star. A neutron star is what remains after a massive star dies, collapses, and crushes matter to densities almost beyond imagination. It can carry roughly the mass of the sun inside a body no larger than a city. Some of them spin so fast and beam radiation so regularly that they flash like lighthouses. Those are pulsars. They are extreme, dense beyond common sense, magnetic beyond earthly comparison, violent enough to strip matter from nearby companions. No one hears the phrase ideal birthplace for a planet and thinks of a pulsar. And yet exoplanet history itself began in a place like that. Long before the public became familiar with hot Jupiters and super-Earths, the first confirmed planets beyond our solar system were found around a pulsar. That discovery shocked astronomy in the early 1990s because it shattered a deeply rooted expectation. If planets could exist around a dead star, then the universe was already stranger than our neat theories suggested. But pulsar planets always sat at the edge of the conversation. They were real, but abnormal. The cosmic exceptions, the eerie footnotes, worlds in radioactive graveyards, more useful for proving possibility than for revealing the ordinary rules of planet formation. PSR J2322-2650b looked at first like another strange entry in that same catalog. It had already been identified years earlier as a companion to a millisecond pulsar. But that older discovery left huge questions unanswered. Was it really planet-like in composition? Was it the leftover core of something larger? Was it a stripped-down star? Was it the ruined survivor of a system that had already lived several lifetimes? That uncertainty is what made the object irresistible. The system belongs to a family astronomers called Black Widow systems. The name is not poetic exaggeration. In these binaries, a pulsar feeds on a smaller companion over time. Matter once flows onto the neutron star, spinning it up faster and faster. Then, the pulsar returns the favor with a punishing wind of radiation and particles, gradually eroding the object trapped nearby. It is less in orbit than a slow execution. So when astronomers looked at PSR J2322-2650b, they were not staring at a peaceful gas giant cruising through space. They were staring at a body locked in a brutal relationship with a stellar corpse. And still, it seemed to have enough mass to remain in the planetary regime. That detail is critical because astronomy has labels for objects, but nature does not care about labels. Below a certain mass, we tend to call something a planet. Above another threshold, it begins to look more like a brown dwarf or stellar remnant. But PSR J2322-2650b sits in a zone where classification is not the real problem. Origin is. If it formed like a normal gas giant, the environment seems absurd. If it formed from the stripped remains of a star, its chemistry becomes hard to explain. Either path leads to trouble. That was the stage before Webb arrived. Scientists expected something strange, yes, but strange within limits. Maybe a battered atmosphere, maybe an unusual temperature pattern, maybe evidence of tides and radiation shaping the planet's brightness as it orbited. What they did not expect was a chemical fingerprint that seemed to reject every comfortable version of the story at once. Webb observed the object across an entire orbit, watching the faint thermal glow change as different portions of the world rotated in and out of view. This was a rare advantage. Normally, exoplanet astronomers struggle because the star dominates the scene. Here, the pulsar emits mostly high-energy radiation like gamma rays, essentially invisible to Webb's infrared instruments. That meant the telescope could study the planet's emission with extraordinary cleanliness. Imagine trying to examine a firefly while someone shines a stadium floodlight in your face. Then, imagine the floodlight is suddenly gone while the firefly remains. That is the gift this bizarre system offered Webb. And when the data came down, the spectrum did not look like a standard hot Jupiter at all. Astronomers expected familiar molecules, the usual suspects seen or sought in exoplanet atmospheres: water vapor, methane, carbon dioxide. Instead, they found evidence for molecular carbon, especially C3 and C2, in an atmosphere apparently dominated by helium and carbon. That is not a minor tweak, that is a completely different chemical world. On Earth, carbon is the backbone of life. In stars, it is a product of nuclear burning. In giant planets, it exists, but not like this, not stripped so cleanly of oxygen and nitrogen that carbon remains unusually free to bind to itself. According to the Webb team, among the roughly 150 planets studied spectroscopically in and beyond our solar system, none had shown detectable molecular carbon like this. That is when the planet stopped being merely weird and became deeply unsettling. Because chemistry is biography. An atmosphere is not just weather, it is memory. It records formation, migration, heating, loss, collision, chemistry, and survival. If a world wears a sky dominated by helium and molecular carbon, then somewhere in its history, ordinary pathways were denied and extraordinary ones were favored. The team also found that the planet is ferociously close to its host, only about 1 million miles away. Earth sits roughly 100 million miles from the Sun. This world completes a full orbit in just 7.8 hours, a year that is shorter than a workday on Earth. At such proximity, the pulsar's gravity does not merely tug, it distorts. Models of the brightness changes suggest the object is being pulled into a lemon-like shape by tides, not spherical, not stable-looking, but stretched by the relentless gradient of gravity across its body. And then there's the temperature. The coldest parts of the night side are estimated around 200 degrees Fahrenheit. The hottest regions of the day side can reach around 3,700 degrees Fahrenheit. Under pressures deep inside, researchers say carbon could potentially crystallize into diamond. In the upper atmosphere, soot-like clouds may drift through the sky. It sounds like mythology dressed as astrophysics, but the real shock was still forming inside the scientific argument. Because if this object is truly so carbon-rich, Then two explanations immediately start fighting each other, and both seem inadequate. The first says it formed like a planet, perhaps from a disk, perhaps in some wildly altered environment, perhaps before the star died. But standard planet formation does not naturally produce such an atmosphere in such a system, not with carbon ratios this extreme, not in a place scorched and reshaped by a pulsar. The second says it used to be something more star-like and then got stripped down over time by the Black Widow process. That is tempting because Black Widow companions are expected to be carved apart by the pulsar. But here again, the chemistry resists the idea. Stellar nuclear processes do not simply hand you a neat, nearly pure carbon-dominated atmospheric story. Too much of the expected mix appears to be missing. So the planet does not comfortably behave like a planet, and it does not comfortably behave like a stripped stellar core either. This is where sensational headlines say it breaks physics. That's not quite true. What it really breaks is confidence. Modern astrophysics is built not only on equations, but on pathways. We think stars form this way, disks cool that way, planetary atmospheres inherit certain ingredients, companion stars lose mass along somewhat predictable lines. Most discoveries stretch those pathways. PSR J2322-2650b does something more humiliating. It stands in the middle of them and asks whether the pathways were ever broad enough to include the full imagination of nature. The second revelation came when scientists tried to understand the planet not just chemically, but dynamically. The atmosphere does not appear static. Webb's data indicates strong westward winds, another clue that this world belongs to a regime unlike the hot Jupiters orbiting ordinary stars. The paper describes ultra-fast rotation under external irradiation, pushing exoplanet dynamics into territory that had barely been observed before. In other words, this is not simply a familiar gas giant placed in an unfamiliar neighborhood. It may be a genuinely new laboratory for atmospheric behavior. That matters because astronomy advances when one object opens a door that theory had left closed. For years, researchers have built models of exoplanet atmospheres around the worlds we could observe best, planets transiting bright, ordinary stars. But now a dead star has handed us something better in one narrow sense. It let Webb isolate the planetary signal without the usual infrared glare. The result is a spectrum so strange that it expands not just a catalog, but the map of what atmospheres can be. And once that map expands, every earlier certainty becomes slightly less certain. How many worlds have we already misread because we assumed the chemistry had to stay within expected limits? How many formation histories look impossible only because we have not found enough survivors from catastrophic systems? How many planetary categories are really just temporary filing cabinets waiting to break? That is why this discovery matters far beyond one object in one exotic orbit. It tells us that planets are not merely decorative side effects of calm, sun-like systems. Worlds can emerge, persist, or be remade in places that seem almost hostile to the concept of a world. A planet can orbit the ashes of a star. It can survive in a region blasted by radiation. It can carry a chemistry that forces astronomers to reopen the oldest question in exoplanet science. What exactly counts as a planet's origin story? And once you ask that honestly, Earth starts to feel different too, not less special, more contextual. Our planet formed inside a comparatively gentle system, under conditions that now look almost merciful. Stable star. Long orbital period. Chemistry that allowed oceans, air, and biology. The more Webb reveals these nightmare worlds, the more clearly we see how narrow the corridor may be between cosmic violence and planetary habitability. There is also a practical consequence. Missions searching for habitable worlds depend on models. We infer atmospheric chemistry from light. We estimate interiors from mass and radius. We reconstruct histories from temperature and orbit. But objects like PSR J2322-2650b remind scientists that nature can generate combinations no modeler would prioritize. If rare systems hide radically unfamiliar atmospheres, then the universe may be more chemically inventive than our current search strategies assume. That does not mean Earth-like life is more or less common because of this one planet. It means humility just became a scientific instrument. and that humility was expensive to build. James Webb was never guaranteed to work. Before it could challenge exoplanet theory, it had to survive one of the most nerve-wracking engineering performances in the history of spaceflight. Its giant sunshield, essential for keeping the telescope cold enough to detect faint infrared light, had to unfold in space with extraordinary precision. Folded for launch, it fit inside a rocket fairing. Deployed, it would stretch to roughly the size of a tennis court. The sunshield alone involved well over 7 in-flight parts and about 150 mechanism assemblies. Roughly 140 release actuators, around 70 hinge assemblies, 8 deployment motors, some 400 pulleys, and about 90 cables all had to work in sequence. Engineers described it as conducting an orchestra from 1,000,000 miles away. Each step had to be commanded from Earth. Each step had to complete before the next could begin. 2 days of deployment stood between triumph and disaster. If any critical part of that chain had failed, the telescope that uncovered this impossible atmosphere might have become one of the costliest cautionary tales ever launched. That human drama matters, because discoveries arrive wrapped in machinery, nerves, and years of people solving problems no one had solved before. Scientists like Michael Zhang, Maya Belesne, Peter Gao, Roger Romani, and their collaborators did not simply receive a cosmic secret. They had to build the tools, fight for observing time, model the geometry, trust the spectrum, and then stand in front of a result bold enough to embarrass existing explanations. When a scientist looks at a dataset and says, in effect, "What the heck is this?" that is not failure. That is the frontier speaking. As for what has happened since, the newest confirmed leap remains the Webb result itself, a full-orbit infrared study showing a carbon-rich, helium-dominated atmosphere, unlike any known around a main-sequence star exoplanet. Since then, follow-up theoretical work has begun exploring whether gravitational tides and pulsar timing can help constrain the internal composition of systems like this one. In other words, the mystery has not been solved, it has only changed shape. That is important to say clearly. There is no verified follow-up proving diamond rain as a settled fact. No confirmed announcement that the object has broken the laws of nature. No final paper closing the case on whether it formed as a planet, a stripped companion, or something in between. The latest honest scientific position is more exciting than certainty. The atmosphere is real enough to force new models, but the full origin story remains unresolved. And that is exactly the kind of discovery that changes a field, not because it answers everything, but because it makes the old answers feel smaller. The next chapter may come from more Webb time, more precise pulsar timing, or the discovery of similar systems that tell us whether PSR J2322-2650b is a freak event or the first visible member of a hidden class. Broader exoplanet missions will help too. NASA's Roman Space Telescope, set to launch in late August 2026, is expected to widen the census dramatically, using microlensing and other methods to reveal vast new populations of worlds, including planets in regimes our current samples barely touch. Roman probably will not solve this one mystery by itself, but it may tell us whether the galaxy is full of stories we have not yet learned how to read. That is the future hanging over this strange world. More data, better models, new categories perhaps, or maybe the collapse of old ones. Scientists may eventually pin down whether the carbon came from a bizarre evolutionary pathway inside a black widow system, from some unimagined form of atmospheric sorting, or from a history so violent that only the chemistry survived to testify. Until then, PSR J2322-2650b remains suspended in that beautiful scientific tension between measurement and meaning. We know enough to be astonished. We do not yet know enough to be comfortable. And maybe that is why this discovery lands with such force. It began with the feeling that something impossible was happening right now. A planet around a dead star. A shape no child would draw. A sky built from ingredients that refused to fit the recipe. A telescope finding clarity only to produce a deeper confusion. But maybe that is the wrong way to see it. Maybe the universe is not becoming stranger. Maybe it was always this strange, and we are only now building instruments worthy of being surprised. The opening mystery was never really whether physics had failed. Physics is doing exactly what physics does. Gravity stretches, radiation strips, chemistry rearranges, time erodes, matter adapts. The real shock is that the cosmos can combine those laws into outcomes that look, from our limited viewpoint, almost fictional. A world in a pulsar's grip can still wear an atmosphere. A companion on the edge of destruction can still preserve a history. A telescope 1,000,000 miles from Earth can still catch the thermal whisper of an object that should have been lost in noise. And when it does, the result is not just another planet. It is a reminder that discovery is not the moment when the universe finally makes sense. It is the moment when we realize how much larger reality is than our best story about it. So somewhere in the dark, PSR J2322-2650b keeps circling its dead star every 7.8 hours under a carbon sky, pulled into an impossible shape, carrying an answer no one has fully translated yet. And James Webb, patient and cold and precise, has made sure we can never look away. If that sense of wonder stayed with you, stay close to this frontier. Subscribe for the next deep journey into the universe, leave a comment with the strangest world you think nature could still be hiding, and share this with someone who still believes space has run out of surprises. Because if one lemon-shaped planet around a stellar corpse can shake our confidence like this, the next discovery may do far more than surprise us. It may redefine what a world